if we put together what we know about linear approximation and what we know about concavity, we can get more information about how the actual value is going to relate to the approximate value. So for example, if your function is concave up, then you know that your actual value is going to be above the graph, aka that the graph of L lies below. So the graph of L is below, so that means that L is going to give you an underestimate of those values. Versus if you are concave down, if you're concave down, you know that L lies above the graph, and so L is going to give you an overestimate. So if you know something about the concavity and you know what your error is, or even if you don't know what the error is, but you can get an approximate for how large it is, you can tell if that is going to be overestimate or underestimate. If you happen to be at an inflection point where you change concavity, you might even have more information about being smaller on one side, lower than the other, if that happens to be the case. So that can tell you, if you do know that the error, you can tell how big or how small the error is, as well as how, if it's under or over, you can actually get a pretty good guess of what the function value should be. Now, based on our experience with the derivatives and slope, linear approximations, we can tie some things together and come up with some important concepts. Let's take a look at this diagram right here. We have some things, note here, we have our original point f of a that we created the linear approximation for. And so our goal is to learn something about the new point x f of x. It's a step size delta x away from a, and the linear approximation value is going to give you an approximate value of the derivative times the change in x, because that's how I'm calculating the y value, just linearly. The actual change in y is just computed from the actual difference of the two y values, but they are approximately equal. They are not equal because there is error, but we can say that the actual change in y is approximately equal to the derivative times the change in x. Okay, so they are obviously not equal. There is some difference between those two functions, but we're using the linear approximation to say that they'll be approximately equal. So instead of looking at the full linear approximation function, I can look at just change in y as it relates to the actual difference in the y values. Okay, so what can we say about change in y as change in x gets very small? So as change in x gets very small, so as it approaches 0, then change in y is going to approach that derivative times change in x. Because as these shrink back down, they're going to the difference between those two things is going to shrink back down as well. Okay, and that gives us this summary right here of some uses of a linear approximation. Sometimes, like I said, we want that full linear approximation function, and you want to use that to approximate an f of x value. So you have your full linear approximation function, like we did before, approximating a function value with that. Sometimes instead of approximating the function value, you just want to approximate the change in y. So instead of approximating f, I could just approximate the change in y, in which case I would just use that last statement, the change in y is approximately equal to the derivative at a times the change in x. There is a cool video that's got some information about the importance of approximation in some real-world contexts, if you want to check that out. Let's take a look at example 2. Approximating the change in the surface area of a spherical ball of ice as it melts from a radius of 4 centimeters to a radius of 3 centimeters. Okay, so I want to approximate the change in surface area. So my goal is to figure out delta S. And delta S is going to be approximately S prime of R times dr, or delta R. Sorry, delta R. Okay, So I can calculate the derivative, and I can calculate the change in r by looking at the two radius values I've got there. Let's get the derivative first. So the derivative s prime of r is going to be 8 pi r if I take the derivative with respect to r here. And so my ice was originally 4 centimeters. So 4 centimeters is our initial condition. It's melting into 3.9 centimeters, but that means that I'm going to be evaluating S prime at 4. And so that gives us 8 pi times 4, or 32 pi. Now for delta r, delta r, I had 4 in my mind there, delta r, if I want to compute that, I might need to subtract, when I compute change, any change is computed with the terminal or final point minus the initial point. So since I was at 4 and I shrunk to 3.9, this is going to be a change of 3.9 minus 4, or negative 0.1. So I do want to keep in mind that because I'm shrinking, I do want delta r to be negative. So it is, if you compute the subtraction in terms of terminal minus initial. So the sign on delta r is going to matter. So is the sign on delta x. We want to get the correct sign on both of those. Okay. I'm not just doing magnitude of that difference, I'm doing that full difference. Okay, so now we can make our estimate that the change in S, again, that delta symbol just means change. We're trying to approximate the change in surface area. It's approximately 32 pi times negative 0.1. So it's approximately negative 3.2 pi cubic centimeters. And if I get a decimal just to compute that, it is approximately negative 3.2 times pi is approximately negative 10.053 cubic centimeters. Okay, so this is a case where I can approximate what the surface area changed by. I know the radius shrunk by 1/10 of a centimeter. I know what the original, because I can compute it, what the original surface area is. I can approximate that the new surface area is 10.05. I don't know for sure without getting out there and actually measuring the new device, measuring the new ball of ice to compute its actual surface area. So that's just our approximate.